Now, let's consider how entropy is related to the unavailability of energy in the universe. It's a very important conceptual discussion that we have to do. I remember Sandra had asked once this question, that how it is related, and here is the answer for that question. So you can consider the case of a heat engine to be more precise in the discussion. So the essential part of a heat engine are two heat reservoirs, right? So one at higher temperature, say at a temperature T1 here. So on the right side, this is at a temperature T1, and the other at a lower temperature. So let me denote that lower temperature as T0. So T0 is the temperature of the lower reservoir, right? T0. So certainly you can see T1 is nothing but our TH. So T1 is greater than T0. Okay. Now, all heat engines absorb heat from the high temperature reservoir and convert a certain amount of heat into work. Okay, and the remaining heat is rejected to the low temperature reservoir, so as usual. So let's assume that this is our engine, the circle. Okay, no, right? It is absorbing a certain amount of Q from the high temperature reservoir, and let's say that it is converting some amount of a portion of this Q into work depending on the efficiency, and the rest will be always rejected to the low temperature reservoir. So in a qualitative way, we can say that the heat that is available in the high temperature reservoir can only be converted into work by the heat engine. Okay, so whatever heat is in the high temperature reservoir can only be converted into useful work, or the heat rejected to the low temperature reservoir is not used up, is not. That is way, in a way, we say that that is getting wasted as far as an engine is concerned. And you usually know, in the case of a heat engine, this low temperature reservoir is either atmosphere. Practically, it is either atmosphere, or it can be some river, water bodies like river, etc. In the case of factories and all, where the hot liquid will be finally flowing out, river, etc. Okay, right? So this heat energy which is in the low temperature reservoir is not actually being available for the heat engine to work on. Okay, so it's a concept. So I can say that the heat available, as far as the heat engine is concerned, the heat available in the high temperature reservoir only can be converted into work. So the heat available in the high temperature reservoir is usually termed as available energy. Remember, this is the meaning of available energy when we use in thermodynamical context. Okay, and now the heat in the low temperature reservoir will be in the unavailable form. That is the way. Heat in the high temperature reservoir will be in available form, and the heat that is in the low temperature reservoir, as far as the heat engine is concerned, is in the unavailable form. Unavailable form. Or we call that one as unavailable energy, unavailable form, of energy. Now, let's see how much heat becomes unavailable, or what is the degradation of energy during the working of a heat engine, and how it is related to the increase in entropy of the particular system or the universe. So, maximum work that can be obtained from a heat engine will be that is obtained from a reversible process, or that can be obtained from a Carnot engine working between the same two reservoirs. That is our Carnot's theorem. Maximum efficiency for an engine is for the Carnot engine for a given pair of reservoirs. So efficiency eta. What is efficiency eta for a Carnot engine? That is related to the temperature. So that is 1 minus TL by TH. This is not 1 minus TL by TH. So here, as per our notations, that will be equal to 1 minus, what is the lower temperature? We have designated that one as T naught. divided by TH is T1. Okay, and what is this efficiency theoretically? Efficiency theoretically is equal to the work output divided by the heat input, right? Work output divided by the heat input to the engine. So this is our engine. Okay, these are the reservoirs, right? So can't you get the work output of this heat engine in terms of T0 and T1? Yeah, therefore maximum work obtainable from any heat engine working between T1 and T0 is given by, we call it as W. W will be equal to, how do you get it? Just cross multiply this equation. So it will be equal to simply 1 minus T0 by T1, right? 1 minus T0 by T1 times Q. Okay, so let me call this as equation number 1, right? So this is true only for a reversible idealized engine like the Carnot engine. But you consider any practical heat engine, or a real heat engine, be it a diesel engine or a petrol engine, whatever it is. Okay, there will be always some sort of dissipation. Heat dissipation always occurs in a practical heat engine in the form of conduction from the cylinders, in the form of radiation, all different ways. There will be a lot of losses in the practical heat engine that always lowers the efficiency of that heat engine. So we can say that as far as a practical heat engine is concerned, the temperature of the high temperature reservoir, temperature of the source or the high temperature reservoir cannot be taken as T1. Okay, instead it will be T2 instead of T1. Let me assume that it is T2. Okay, the temperature of the working substance in the cylinder of a practical heat engine will be at a temperature T2, which is always less than T1. T2 which will be always less than T1. Okay, so that is due to the losses. From this one there are some losses, so the entire T1 will not be there. Instead there will be a lower temperature T2, which is practically for the real engine. So let's say that in that case, so T2 is the temperature for a practical engine, T1 is the temperature of the high temperature for a a Carnot engine, and T2 due to losses will be always less than T1. So what will be the maximum work that can be obtained from a practical heat engine? So only what you have to do is that, let me replace this work, that is, let me call this work as W dash. So W dash will be equal to, just what you have to do, just you replace T1 by T2. So that is 1 by T0 by T2 times Q. Okay, so we assume that the same amount of heat is drawn. Okay, so let me say that this is equation number 2. Now comparing 1 and 2, and from the fact that T2 is less than T1, you can see that this W dash will be less than W. Clearly it indicates 1 and 2, or this results, it indicates that W dash will be less than W, and that is a principle. In principle, work output of a real engine for a given heat drawn from the source will be always less than that for a Carnot engine between the two reservoirs. Okay, therefore we can say that when in comparison to a Carnot engine, in comparison to a reversible engine, there is always some loss of available energy, is not, because you cannot obtain the same amount of work. Okay, so during this process there is some loss of available energy, means you are not able to convert complete energy or complete heat into work as that can be done by a Carnot engine. So there is a difference between W and W dash. W is a reversible engine and W dash is an irreversible engine or a real engine. Okay, so the difference is that in the real engine there are some irreversibilities due to dissipation. Okay, so I can say therefore loss of, we consider it as a loss of available energy. Loss of available energy. Loss of available energy. How do you calculate in this process? you can calculate it as the difference between W and W dash. So that is equal to W minus W dash. What will be W minus W dash is equal to? That will be, can't we just do that one? So I can subtract 2 from 1. So what are the common factors over there? Yes, of course, T0Q. Okay, that is common factor. So what I'm doing is that I'm writing it as, I want to bring in entropy. So I'll be writing it as Q divided, let me take this Q inside the bracket and T0 outside. Okay, so Q divided by 1 and 1 will get cancelled. Q divided by T2. Okay, so by when you take the minus, this negative will become plus and this will be minus itself. Okay, so Q divided by T2 minus Q divided by T1, Q divided by T2 minus Q divided by T1 times T0, times T0. That will be on subtracting 2 from 1. 1 that will get cancelled, of course. Yeah. Now I have just rearranged. So what is this Q by T2? By definition, Q by T2 is nothing but S2, is it not? That is S2. So that is equal to, finally equal to S2 minus S1. S2 minus S1. Okay, Q by T1 is S1 into T0. Okay. Now, where S2 and S1 are the entropies, corresponding to T2 and T1. Okay. See, you know that this T2 is less than T1. Okay. As per our assumption, T2 is less than T1 due to the dissipation. So, what about then Q by T2? Won't this Q by T2 be greater than Q by T1? Yeah, because Q is the same, numerator is the same. So, what I can say is that since T2 less than T1, I can say S2 will be greater than S1. Or what about S2 minus S1? S2 minus S1 will be positive. So this S2 minus S1 is positive. And temperature is never negative, you know. Okay. So what I can write this one, since S2 minus S1 is positive, I can call this one, there is a gain in entropy. Increase in entropy. So I will write that this is a gain in entropy. S2 minus S1 is not a loss in entropy. Instead, it's a gain in entropy into T0. See that? Therefore, what is our conclusion? Loss of available energy or increase or in the loss of available energy during the working of a heat engine in comparison to a reversible heat engine. Remember, it's a number. Okay, that is equal to gain in entropy into T0. What does it conclude? We conclude that right, entropy of a system, as the entropy of the system goes on increasing, means when this gain goes on increasing, T0 is a constant as far as we concern, right? Okay, so as the gain in entropy increases, means as the entropy increases as the outcome of a process, what will happen? The loss of available energy increases. Loss of available energy increases means what? The amount of unavailable energy will be going on increasing, or the amount of available energy will be going on what? Decreasing. Okay, so our conclusion is that entropy of a system is a measure of the unavailability of energy from it, or that is the reason why we usually relate entropy with unavailable energy or entropy with available energy. You can do in other way also. So more the entropy change, that's the idea. More the entropy change as a result of a process, more the entropy change, greater will be, or more will be the unavailability of energy. That's the conclusion. Or it's actually entropy is related to the quality of energy in the universe. That's the way in which you have to understand. It's a conceptual point that I want to specify. Entropy can be related to the quality of energy in the universe. Remember, total energy, it doesn't relate to the total energy. Total energy is always conserved. Okay, there is no any loss in total energy, but with the increase in the entropy of the universe, as a result of all natural process, we have concluded that the entropy of the universe is going on increasing. So how does it affect the quality of energy? The effect is that the amount of available energy to be used by a heat engine, which can convert into practical work, will be going on reducing, and that is the result. And therefore we consider the entropy of a system as a measure of the unavailability of energy from the system. Or this concept is usually regarded as the principle of degradation of energy. What is it? Degradation? You know, degradation, the word we will use when something we talk about related to the quality of something, right? So that is why we usually say that conceptually entropy is related to the quality of energy. Quality means whether it is available for us or it is not available. So more the entropy of the universe, lesser will be the amount of energy available for conversion by a heat engine. Okay, so that's a very conceptual understanding. So hence second law is sometimes referred to as the law of dissipation or law of degradation of energy, principle of degradation of energy. Okay, so it answers the questions. So our conclusion is that as a result of irreversible processes, or as a result of natural processes which are inherently irreversible in nature, the entropy of the universe goes on increasing, or in a sense the amount of available energy will be going on decreasing as a result of the all natural process, and it has got a very serious consequence that we'll be discussing in the next session. Thank you.